All right, today we're going to be looking at section 3.2, it's measures of dispersion. Dispersion just tells you kind of how spread out your system is. So last section we talked about the center, like the mean, median, mode, the average. So now we're going to talk about how spread things are. So we have two sets of data here as an example, and we're going to make some charts and some displays. One, you can see there's a lot of variability, and then in one of them they're more clumped together. And one of the things we'll do is find the standard deviation, the range, and the variance that will tell us how spread out things are. So R is the range. To find the range, you're going to take the largest value, you're going to subtract the smallest value, and that will give you the difference between the biggest and smallest. So that's one measure of dispersion. And then the standard deviation. So this is a more complex and one of the most used measures of spread. So part of this formulation, we're going to find the average. Okay, so mean, or mu, is the population mean, x bar is the sample mean. You will find the average. The average should be somewhere in the middle. It's going to be smaller than some values. It's going to be larger than some other ones. You're going to take each individual value and subtract the mean. Okay, so we should see a table with this. So this is a full formula. So you're going to take each value, subtract the mean. Some of them will come out positive, some of them will come out negative. Once you get those values, you're going to add them up. Okay, the sum of those differences should always be 0. So we can't do anything with 0. So what we do instead is we take those differences and we square them. So here you see that in the formula. We're going to square those differences so that we get positive numbers. Okay, so we'll get a bunch of positive numbers. We're going to add all those numbers up, divide by the total number of values we have, and then we're going to take the square root of it to get back a positive value. So this is the formula for standard deviation. It's a very intricate formula. I think we will have an example spelled out, and then I will also show you how to do that with the calculator. It does it really quickly. So here's an example of the data. They take all of these numbers here, add them up, find the average. So here's the average, 79. Then you take each of those numbers and you're going to subtract the mean. So you subtract 79. So you get 3. This one's going to give you a negative number, some positive, some negative. If you add up all of these numbers, you get 0. So that doesn't tell us anything. So instead of just adding up those numbers, we take those numbers, we square them, so that's the squared part, and then I add up all of those numbers. Okay, so that gives me the sum of the squares, sum of the differences squared. Once we get the sum of the differences squared, we're going to divide that by n, by the total number of items we have, and then once we get that number, we take the square root. Okay, and that gives us our standard deviation. If we don't take the square root, this number is called the variance. And so S is just the sample. This symbol here that we were looking at is called sigma. Sigma is for the population standard deviation. Both of these mean standard deviation. I don't think I saw that definition. Yeah, here it is right here. So this is sigma. Do they spell that out? Yes, right here. This lowercase Greek sigma. So this symbol is sigma. All right. And then we also have, it's the same calculation for standard deviation. It's just one is the population mean, one is the standard deviation mean. Now there is one difference. Because we're dealing with a sample and samples will vary, we don't divide by n, we divide by n minus 1 when we're doing the sample. Okay. N minus 1 is something we call degrees of freedom. So that tells us the number of variability that we might have is, we get to pick like one of those values and the rest of them will be more varying in a sense. So, so you got some more simple examples showing you how to compute standard deviation. Standard deviation will always be positive. Okay, we always talk about the spread from the mean in a positive way. So all this is some good reading. Tell you about how to read and interpret deviations and what that means. So variance, here's the definition of variance. It's basically the square of the standard deviation, so it's what you get before you take the square root off. And that's some more description of standard deviation. So now, here is mainly how we will use standard deviation with this empirical rule. So the empirical rule is when you have a bell-shaped curve. This is very, very important. I definitely would say write this down, have this somewhere to go back over. So standard deviation, when you have a bell-shaped curve, okay, that means all your data is roughly bell-shaped. So you have the average. The average goes right in the center. So like some people are going to score below the average, some people are going to score above. Once you find the standard deviation, if you have an average and you subtract the standard deviation and you add the standard deviation to that average number, you will get an open interval, and that interval contains about 68%. So that's what this is saying right here. From this bar to this bar, a little more than half of your data will be within one standard deviation of the mean. Now, if you start from the mean and you add 2 standard deviations, so that's what the 2 sigma is, and you subtract 2 sigma, you get another interval, and within 2 standard deviations is 95% of the mean. So 95% of your data are going to be within 2 standard deviations. And then if you do 3 standard deviations, so 1, 2, 3 here and 3 here, then you will get 99.7%. So from end to end is 100%, but this is telling you the breakdown because it is symmetric, which means half is on one side, half is on the other side. So if 68 is in the middle from here to here, then divide that by 2 and you get 34 each. Now with the next 2, it's 95. Okay, and I'll try to do a video of this. So from 2 standard deviations out to 2 on the other side is 95. Well, we already got 68 counted in the middle, so if you do 95 and you take away 68, that will leave you with 27 for this and this. You divide that 27 by 2 and that gives you your 13.5. And you do the same for the third. So this is the really good breakdown of the bell curve. It tells you each little section, and you can count how many standard deviations above or below to find that percentage. We'll use that. That's very important. All right, so here's just some more examples in how it would be used in a problem scenario. Again, some more examples telling you greater than. So now we also have Chebyshev's theorem. So Chebyshev's theorem is more of a rough estimate of any distribution, any shape. Doesn't have to be bell shape like empirical rule. So any distribution, any shape will follow this for Chebyshev's theorem. 1 minus 1 divided by k squared, where k is the number of standard deviations from the mean. So k is telling you k standard deviations of the mean. So if we're talking about 1, then we got 100% or 0. We don't have 1. It only works when k is greater than 1. So like if you plug 1 here, it wouldn't give you anything. You have a 1 minus 1 times 0, wouldn't tell you anything. So it only uses it for values of k greater than 1. So if you have 2 standard deviations, let's go to the next page and see if we can see some of those calculations. So you plug in a 2 here, you get 1/4. So 1/4 times 100 is 75%. So 75% is a little bit bigger than what we got from, no, it's smaller. It's more conservative because they're not as sure. It's less certain. But they're saying at least 75% or more is within that. And with the bell-shaped curve, we know that it's 95%. So it's saying at minimum 75 or above. So that would include the 95%. And if you have three standard deviations from the mean, it's going to tell you 88.9, which the bell curve told us 99.7, so this much or more. So that's Chebyshev's theorem. You can use that anytime, and with that, we'll just jump over to MyMathLab and start doing some practice problems.